Tonight we're going to explore 7 rules that govern all of reality. Rules so strange that the physicists who discovered them refused to believe their own mathematics. Rules that were tested and retested and verified in thousands of independent laboratories across nearly a century of relentless scientific effort, and still made no logical sense to the people who confirmed them. Rules that work spectacularly flawlessly, with a precision no other theory in the history of science has ever matched, and yet rules that no one on Earth can tell you why are true. These are the 7 fundamental laws of quantum mechanics, and by the end of tonight, you're going to understand why the universe, at its smallest scales, is completely alien to every intuition you have about how things work. You're going to understand why the greatest minds of the 20th century called quantum mechanics disturbing, incomplete, and philosophically unacceptable. And you're going to understand why, despite all of that, quantum mechanics is the foundation of almost everything in the modern world, from the transistors in every computer to the fusion reactions in every star in the sky. Before we get started, if you love exploring the depths of science and space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The story of quantum mechanics doesn't start in a high-energy particle accelerator. It doesn't start with a genius having a revelation in a dream. It starts with a problem that scientists in the late 1800s thought was almost embarrassingly simple. They wanted to understand why hot objects glow. This was called black-body radiation, and everyone knew it happened. Heat a piece of iron, and it starts to glow red. Heat it more, and it turns orange. Heat it further, and it goes yellow, then white. The relationship between temperature and color was beautifully regular, predictable, measurable. All that was needed was a mathematical description. But every attempt to derive that description from the known laws of physics ended in catastrophe. When physicists applied the established equations of thermodynamics and electromagnetism to a hot glowing body, the mathematics predicted something monstrous. It predicted that the hot object should emit infinite energy at high frequencies. Not a great deal of energy, not more than we can measure. Infinite. An object as ordinary as a piece of iron, heated in a forge, should, according to the best equations of 19th century physics, instantly obliterate everything around it with an infinite torrent of high-frequency radiation. This was called the ultraviolet catastrophe, and it was not a small discrepancy to be refined away with better measurements. It was a fundamental, catastrophic breakdown of the entire edifice of classical physics. In 1900, a German physicist named Max Planck found the fix. But the fix troubled him so deeply that he spent the next decade trying to undo it. He found that if he assumed energy didn't flow in continuous streams, the way water flows through a pipe, but instead came in discrete little packets, fixed minimum amounts that couldn't be subdivided, when the catastrophe disappeared. Maths became perfectly well behaved. The predictions matched the measurements exactly. He called these minimum packets quanta, singular, quantum. Planck believed, or tried to believe, that the quantum was just a mathematical artifact, a clever trick for making the equations work, not a description of physical reality. He hoped someone would come along and show that energy was actually continuous after all, and the quantization was just an approximation that happened to give the right answer. Nobody ever did. Nobody has in over a century.
5 years later, in 1905, a 26-year-old patent clerk named Albert Einstein, working in Bern, Switzerland, with no laboratory and no university position, took Planck's idea and used it to explain something completely different. The photoelectric effect, the observation that certain metals eject electrons when you shine light on them. The strange thing about the photoelectric effect was that it didn't behave the way waves were supposed to behave. A wave of higher intensity carries more energy, so a more intense beam of light should eject electrons more easily. But that's not what happened. A very dim beam of blue light ejected electrons. A very intense beam of red light ejected nothing at all. The color mattered, the intensity didn't. Einstein explained this by proposing that light itself came in quantum packets. He called them photons. Each photon carries an amount of energy determined strictly by its frequency and its color. A blue photon carries more energy than a red photon, regardless of how many photons there are. The intensity of a light beam is just the number of photons per second, not the energy per photon. So a very bright red beam has many photons, but each one has too little energy to knock an electron loose. A single blue photon has enough. That's why color mattered and intensity didn't. This was the second crack in the classical framework. The first had been Planck showing energy was quantized. Now, Einstein was showing that light, which Maxwell had proven was an electromagnetic wave, and which showed all the classic wave behaviors of diffraction and interference, was simultaneously a stream of particles. Both things were true. Light was a wave. Light was made of particles, both at the same time. This was conceptually incoherent by every standard of classical physics. A thing is either a wave, continuous, extended, spread out through space, or a particle, discrete, localized, existing at a point. It cannot be both. The mathematics didn't care.
The experiments confirmed Einstein's prediction to extraordinary precision. For his explanation of the photoelectric effect, not his work on relativity, Einstein won the Nobel Prize in Physics in 1921. The Nobel Committee explicitly noted that the theoretical explanation was still controversial. Even in 1921, the physics community hadn't fully accepted that light was made of particles. But the evidence accumulated and accumulated and accumulated. Before we dive into the 7 laws, we need a moment with the people who discovered them. Because the history of quantum mechanics is not just a history of equations. It is a history of intelligent, rigorous, careful scientists confronting something that made no sense. Something that defied every expectation. Something that, at each turn, refused to fit into any framework they had. And discovering that the framework needed to be abandoned entirely. Niels Bohr, the Danish physicist who became the philosophical center of the quantum revolution, once said that if you are not shocked by quantum mechanics, you have not understood it. He wasn't speaking casually. He was speaking as someone who had spent decades trying to understand it and had concluded with intellectual honesty that quantum mechanics was simply not comprehensible in classical terms. That the attempt to find a classical story behind quantum mathematics was a mistake. That you had to accept mathematics as the reality and let go of the need for a more intuitive picture. Albert Einstein never accepted this. He and Bohr debated quantum mechanics for decades, at conferences, in letters, in thought experiments. Einstein kept proposing scenarios that he believed would catch quantum mechanics in a contradiction. Bohr always found the answer. The debates were among the most intellectually rich exchanges in physics history. And in the end, the experiment sided with Bohr.
But Einstein's resistance was not irrationality, it was intellectual courage. He saw more clearly than almost anyone how radical the implications of quantum mechanics were. How much it demanded that physics be abandoned, and he wasn't willing to abandon it without exhausting every alternative,
He was wrong, but he was magnificently wrong, and the experiments that proved him wrong are among the most beautiful in science. Paul Dirac, who combined quantum mechanics with special relativity and predicted the existence of antimatter, which was then discovered exactly as he predicted from an equation, said that quantum mechanics was the result of taking mathematics more seriously than intuition. That mathematics told you what the universe was like. And if the universe turned out to be unlike anything in your experience, the correct response was to update your experience, not your mathematics. Antimatter, predicted from an equation, discovered in a cloud chamber in 1932, exactly where Dirac's mathematics said it would be. That's what quantum mechanics has been doing for 100 years, predicting things that seem impossible, and then those things are found, exactly, every time. Tonight is a tour of 7 of the most fundamental, the most strange, the most verified, the laws that are most often cited when physicists say, this is where classical physics ended and something radically, permanently, unsettlingly new began. Let's go through them one by one. Stay with each until it lands. Don't rush past the strangeness. The strangeness is the truth. The first law is wave-particle duality, the discovery that everything that exists, light, electrons, protons, atoms, and even entire molecules, simultaneously behaves as both a wave and a particle. Not sometimes one and sometimes the other, both at the same time, all the time, until the act of observation forces it to be one or the other. This is not a philosophical position. It's no metaphor for our ignorance. It is a quantitatively verified experimental fact that has been confirmed in laboratories around the world for the better part of a century, most recently with objects large enough to see in an electron microscope. Let's start with the most famous demonstration of this law, the double-slit experiment. Richard Feynman, one of the greatest physicists who ever lived, called it the only mystery in quantum mechanics. He said it was the one phenomenon that quantum mechanics describes perfectly, and which has no classical explanation whatsoever. If you understand it deeply, you understand everything strange about the theory. Imagine a solid barrier with 2 narrow vertical slits cut into it. Behind the barrier is a detection screen. Now we fire things at the barrier one at a time. Start with something classical, baseballs. A baseball thrown toward the barrier either goes through the left slit or the right slit. On the screen you get 2 stripes, one behind each slit. This is what particles do. Now try it with water waves. Let ripples hit a barrier with 2 gaps. The waves pass through both gaps simultaneously and spread out on the other side. The 2 wave fronts then overlap. Where 2 peaks meet, they add together. Where a peak meets a trough, they cancel. The result is a regular pattern of alternating bands that is called an interference pattern. It is the definitive signature of a wave. Not 2 stripes, many stripes. Now fire electrons at the double-slit barrier. Electrons are particles. They have mass. They have a definite charge. Every detector ever built detects them as a single point. They are discrete. They are individuals. You fire them one at a time. Each electron hits the screen at one point. A dot appears. You fire another dot. They seem completely random. But as you fire thousands of electrons, a pattern emerges on the screen. Not 2 stripes, an interference pattern. Many alternating bands are mathematically precise. The electrons, each discrete particle that hits the screen at a single point, are collectively building a wave pattern. A pattern that can only arise through interference. A pattern that requires each electron to somehow pass through both slits at once and interfere with itself. Impossible, and yet there it is. The experiment was performed with single electrons fired sequentially with long gaps between them. Each electron is alone. It can't possibly interact with the previous one. The detection screen sits empty for minutes between electrons. And still, dot by dot, hit by hit, the interference pattern assembles itself. One electron at a time, producing a wave pattern. Each electron goes through both slits. It has to. The mathematics says so. The experiment confirms it. In 2002, Physics World magazine polled readers to identify the most beautiful experiment of all time. The double-slit experiment with single electrons came first. Akira Tonomura and colleagues at Hitachi in the 1970s and 1980s performed the experiment with extraordinary care. They built an electron source so well controlled they could guarantee emission of individual electrons, one at a time, with long intervals between them. Then they watched the screen. For the first few electrons, just 3 or 4 or 5, the screen showed what looked like noise, random dots, no pattern. Each electron landed at a single point, confirming its particle nature. After about 100 electrons, there was still just a scatter of dots.
Maybe slightly denser in some regions, but nothing definitive.
After 3,000 electrons, something began to emerge. Very faint suggestions of vertical bands. After 20,000 electrons, the pattern was unmistakable. Clear, regular, alternating bands. The full, multi-banded, mathematically precise interference pattern. And each individual electron throughout the experiment had been completely alone. Tonomura's team captured this experiment on film. You can watch it online. You can see the random-looking dots in the early frames. You can watch the pattern gradually emerge, dot by dot, hit by hit, a wave pattern built from individual particle detections. It is one of the most beautiful things in science. Now let's do something about the experiment. Let's put a detector right at the slits. Not to interfere with the electrons, we'll make the detector as gentle as physically possible. We just want to know, which slit did this electron go through? The moment the detector is placed, the interference pattern disappears. Immediately, completely. As soon as information about which slit the electron passed through becomes available, not when it's recorded, not when it's read, but simply when it exists somewhere in the universe, the interference vanishes. The electron stops behaving like a wave and starts behaving like a particle. 2 stripes appear on the screen. The mere availability of information changed the physical outcome of the experiment.
This result has been verified with extraordinary care. The detector doesn't need to physically touch the electron. It doesn't need to exchange large amounts of energy. The only thing that matters is which path information is in principle detectable. If it is, no interference. If it isn't full interference. Every time, without exception. And the effect doesn't stop with electrons. It applies to photons, to neutrons, to entire atoms. In 1999, Anton Zeilinger's group at the University of Vienna performed the double-slit experiment with Buckminster fullerene molecules, carbon-60 structures made of 60 carbon atoms arranged in a soccer ball shape. Each molecule is large enough to be visible in an electron microscope. The interference pattern appeared. In 2019, the same group used molecules containing over 2,000 atoms. Still, the interference pattern appeared. The boundary at which quantum behavior ends and classical behavior begins is not a matter of size, it's a matter of coherence. The speed at which the quantum system loses its phase coherence through interaction with its environment. Large objects decohere so fast through so many simultaneous interactions with air molecules and photons and electromagnetic fields that their quantum wave nature is for all practical purposes instantly destroyed. The quantum effects are there in principle for everything.
For you, for the chair, for the planet, they're just undetectably small. For electrons and photons and atoms, they are not undetectably small. They are the dominant feature of existence. Every particle you have ever observed, every atom in your body, every photon of starlight that has ever touched your eyes, is simultaneously a wave smeared across space and a particle that lands at a definite point. Until it's measured, it's a wave. At the moment of measurement, it's a particle. And in between the silence, where no one is watching, it is both. This is not a defect of our instruments.
This is not ignorance dressed as physics. So is the universe. Light decides what it is based on whether you're watching. So does everything else. The second law is the Heisenberg uncertainty principle, the discovery that you can never simultaneously know both the exact position and the exact momentum of any particle. Not because our gauges are too clunky, not because we don't have technology yet, not because the universe is hiding something, but because the universe does not contain that information to be found. Position and momentum cannot both be precisely defined at the same time, because at the quantum level, the universe does not simultaneously define them. Werner Heisenberg derived this in 1927. He was 25 and working in Copenhagen with Niels Bohr. He wasn't trying to make a philosophical statement about the limits of knowledge. He was trying to understand what quantum mechanics actually implied about measurement. What he found changed physics permanently. The principle states this: the product of the uncertainty in a particle's position and the uncertainty in its momentum can never be smaller than a fixed constant. That constant is related to Planck's constant, the same quantity that appears in every quantum formula. It is approximately 1.055 times 10 to the negative 34 joule seconds. An almost incomprehensibly small number, but incomprehensibly small is not zero. If you pin down a particle's position with great precision, if you know exactly where it is, then its momentum becomes wildly uncertain. You have no idea how fast it's moving or in what direction. Conversely, if you know its momentum with great precision, if you know exactly how fast it's moving, then its position becomes completely undefined. This is not a practical limitation. This is a fundamental structural feature of quantum reality. It holds equally well for the most exquisite hypothetical measuring device you could ever imagine. The limitation is not in the measurer, it is measured. Where does this uncertainty come from? From the wave nature we discovered in Law 1. Because particles are waves, and waves have an inherent, inescapable conflict between localization and definite frequency. Think about a pure, perfectly sinusoidal wave, the kind you draw in a textbook, extending infinitely in both directions with perfect regularity. That wave has a perfectly defined frequency. You know its momentum with absolute precision. But where is it? It extends everywhere. It has no location. Its position is completely undefined. Now think about a highly localized wave. A sharp spike in one place, essentially zero everywhere else. That wave has a very definite location. But a sharp spike is not a pure sine wave. To create a spike shape, you have to add together an enormous number of different sine waves with different frequencies. The sharper the spike, the more different frequencies you need to add. But adding more frequencies means the momentum is spread across a wide range. You know where it is, but not how fast it's moving. This is called the Fourier uncertainty relation, and it is a mathematical fact about waves that has nothing to do with physics specifically. It's true for ocean waves. It's true for sound waves. It's true for any wave. And since quantum particles are waves, it's true for them.
The Heisenberg uncertainty principle is a direct mathematical consequence of the wave nature of matter. But its physical consequences are extraordinary. The most important consequence is one that shocked physicists when it was first understood. Atoms are stable. In classical electromagnetic theory, an accelerating charge radiates energy. An electron orbiting a proton is constantly accelerating. It's curving continuously around its orbit, so it should constantly radiate energy. As it radiates energy, it spirals inward. The spiraling gets faster, the radiation gets stronger, the orbit gets smaller, and within about 10 nanoseconds, the electron crashes into the proton. Classical atoms should collapse essentially instantly. They should not be stable. They should not exist. But here you are, made of atoms. The Heisenberg uncertainty principle saves them.
Imagine trying to confine an electron very close to the proton. Its position would be very precisely defined. But the uncertainty principle demands that a precisely defined position comes with a wildly uncertain momentum. A wildly uncertain momentum means the electron has an enormous range of possible kinetic energies, and on average, an enormous amount of kinetic energy. Enormous kinetic energy means the electron is moving very fast. Moving very fast means it doesn't stay near the proton. It escapes. There is a specific distance from the proton at which these two effects, the electrical attraction pulling the electron inward and the kinetic energy driven by quantum uncertainty pushing it outward, exactly balance. That distance is the Bohr radius, about 0.529 angstroms.
That's the radius of the hydrogen atom. It is fixed, universal, derivable from the uncertainty principle, and it cannot be made smaller without violating the principle. The uncertainty principle is what keeps atoms from collapsing. It is the reason solid objects are solid. It is the reason you don't fall through the floor. There's a second conjugate pair beyond position and momentum: energy and time. The energy-time uncertainty principle says that the more precisely you know the energy of a quantum system at a given moment, the less precisely you know when that energy state exists. The shorter the time interval over which something happens, the more uncertain the energy during that interval. This has a stunning consequence for empty space. Imagine a perfect vacuum. No particles, no radiation, nothing. The energy should be exactly zero. The quantum mechanical calculation says otherwise. If a region of space exists for a finite time, and all regions of space do, its energy cannot be exactly zero. There must be some irreducible uncertainty. And since space doesn't pop in and out of existence, this uncertainty manifests as random fluctuations. Tiny bursts of energy constantly appear and disappear in the vacuum, lasting for incredibly brief moments before vanishing again. These are called quantum vacuum fluctuations. They are not theoretical constructs invented to save the equations. They are physically measured. The Casimir effect demonstrates them directly. Place two uncharged metal plates extremely close together in a vacuum, within a micrometer or less. If the vacuum were truly empty, there would be no force between them. But the vacuum fluctuates. The space between the plates is so narrow that only certain vacuum fluctuations fit inside. Longer wavelength fluctuations are excluded. There are more fluctuations outside the plates than between them. The imbalance creates a net inward force. The two plates are pressed toward each other by the pressure of quantum vacuum energy. Hendrik Casimir predicted this in 1948. Measured experimentally in 1997 with high precision. The force exists. It has been measured in hundreds of experiments. The vacuum is not empty. Empty space is filled with energy, quantum energy, fluctuating, restless, constantly arising and vanishing energy. Because of the uncertainty principle, because nothing in the quantum universe can be perfectly still, because the universe at its deepest level is fundamentally, irreducibly restless. The atom in your finger, that is, at this moment, part of the most chemically stable bond in the molecule it belongs to, is still vibrating. Not because anything external is disturbing it, because the uncertainty principle forbids complete stillness. A perfectly stationary atom would have a perfectly defined position and zero momentum. But that would violate the uncertainty principle. So the atom vibrates, always, even at absolute zero temperature, even in a perfect crystal. These are called zero-point vibrations, and they are experimentally measurable in precision spectroscopy. Helium-4 cooled to the lowest temperature ever achieved in a laboratory remains liquid. It refuses to freeze. The zero-point energy from quantum uncertainty keeps its atoms moving too fast to lock into a crystal lattice. Only under enormous pressure can helium-4 be made solid. The quantum vacuum, the stability of atoms, the zero-point energy of crystals, all of it is rooted in one principle. The universe itself does not simultaneously define both where something is and how fast it's moving. And in that fundamental incompleteness, matter as we know it is made possible. The act of knowing one thing makes another thing unknowable. The universe is built on this constraint, and we would not exist without it.
The fourth law is quantum entanglement. The discovery that two particles, once they've interacted in the right way, become permanently linked. Not by a physical tether, not by any force we know, by something more fundamental than force. They share a single quantum state. And when you measure one of them, no matter where in the universe the other one is, its measurement outcome is instantly determined. Not after some delay for a signal to travel, instantly. Einstein called this spooky action at a distance. He said it was impossible. He dedicated years of his intellectual life to proving it must be an artifact of an incomplete theory. He was wrong. Let's understand entanglement precisely. Two particles interact in a way that creates a correlation between their quantum states. The simplest example uses spin. Two electrons can be created, for example, by the decay of a parent particle in such a way that their spins must be opposite. By the conservation of angular momentum, if one is spin up, the other must be spin down. The total spin is zero. Before either particle is measured, each is in a superposition of spin up and spin down. Individually, each particle has no definite spin, but their spins are correlated. Whatever one is, the other is the opposite. Now separate the particles. Send one to a detector in Zurich and the other to a detector in Melbourne. Let them travel 10,000 kilometers apart. In Zurich, a physicist measures the spin of her particle. It collapses to spin up. At that same instant, not a fraction of a second later, not after any time for any kind of signal to travel, the particle in Melbourne is spin down. The measurement hasn't happened yet in Melbourne, but the result is already determined. The moment Zurich made her measurement, the entire shared quantum state collapsed everywhere at once. This has been verified in hundreds of experiments. The correlations appear with zero time delay within the experimental precision.
As we discussed in Law 3, Bell's theorem proves that these correlations cannot be explained by any local hidden variable theory. The particles didn't secretly carry predetermined spin values from the moment of their creation. The correlations are genuinely non-local. They arise from a quantum connection that transcends the ordinary separateness of space.
The immediate question is, can we use this to send information faster than light? The answer is no, and the reason is elegant. When the physicist in Zurich measures her particle and gets spin up, she learns that the Melbourne particle is spin down. But what does the physicist in Melbourne observe? He measures his particle and simply gets a random result, either spin up or spin down with equal probability. He has no way of knowing from his measurement alone whether his result is correlated with Zurich or not. Both outcomes look completely random to him individually. The correlation only becomes apparent when Zurich and Melbourne compare notes, and that comparison must happen through ordinary classical means. A phone call, a physical message, all limited to the speed of light or below. The entanglement is non-local. The information is not. The measurement outcomes are random on each side. The correlation is a pattern that can only be seen when the two sides are compared classically. There is no loophole for faster-than-light signaling, but the non-locality is real, deeply, experimentally, indisputably real. In 2017, China's Michia satellite performed the first satellite-based test of Bell's inequalities. Entangled photon pairs were generated on the satellite and beamed to 2 ground stations in China, separated by 1,203 kilometers. The Bell inequality was violated with high statistical significance. The entanglement held perfectly across 1,203 kilometers of open space. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics. The Nobel Committee's citation explicitly stated that the work proves nature is not locally realistic. The universe does not consist of locally defined properties at every point. This is not esoteric. Entanglement is already being harnessed technologically. Quantum cryptography uses entangled particles to create encryption keys that are theoretically unbreakable.
Any interception of an entangled communication disturbs the quantum states the eavesdropper's presence is immediately detectable. This is not a conjectural technology. Quantum key distribution systems based on entanglement are commercially available. China has deployed a 2,000-kilometer quantum key distribution network connecting Beijing and Shanghai. The world's first quantum satellite, Mycia, supports quantum cryptography between ground stations across Asia and Europe. Quantum teleportation uses entanglement to transmit the complete quantum state of a particle from one location to another without the particle physically traveling. The state information is instantly available at the destination through entanglement, with only the classical measurement results needing to travel through ordinary channels. Quantum teleportation has been demonstrated over hundreds of kilometers. It will be a foundational technology of the quantum internet. But beyond technology, entanglement has philosophical implications that go very deep. It means the universe cannot be divided into truly independent parts. Any two quantum systems that have ever interacted remain, in a technical sense, part of one quantum state. The entire observable universe, from the moment of the Big Bang, has been interacting with itself for 13.8 billion years. Every particle that has ever interacted with another particle carries some remnant of that interaction in its quantum state. The universe at the quantum level is one entangled whole. The separateness that feels so fundamental to everyday experience, the fact that you are here and a star in another galaxy is there, completely distinct, is at the quantum level an approximation. A very good approximation for all practical purposes, but not in the deepest sense true. At the deepest level, the universe is not separate things with separate properties that sometimes affect each other through forces. The universe is one quantum state, entangled across all of space and time, that we experience locally as separate things. That is not poetry. That is what quantum mechanics says. That is what Bell's theorem proves. That is what the Nobel Committee confirmed in 2022.
The universe is one entangled whole.
The seventh and final law brings together everything we've explored tonight and takes it to its ultimate conclusion: quantum non-locality. The discovery that the universe does not consist of locally defined physical properties existing independently of observation. The universe is not a collection of things sitting in definite states, in definite places, waiting to be observed. The universe is a quantum structure in which locality, the idea that what happens here has nothing to do with what happens there, is not fundamental. This is the conclusion that follows from combining the previous 6 laws. From wave-particle duality, which shows that particles spread through space as probability waves. From superposition, which shows that quantum properties have no definite values before measurement. From entanglement, which shows that correlated particles share a quantum state that cannot be described locally. And from the observer effect, which shows that measurement creates, rather than reveals, physical properties. Before the 20th century, physics operated on what philosophers call local realism. 2 principles. The realism part. Physical objects have definite properties that exist independently of whether anyone observes them. A table has a definite position and mass, whether or not you're looking at it. A particle has a definite spin, whether or not you've measured it. Reality is real, independent of observers. The local part. The physical state of any region of space is determined only by what's in that region, and it can only be influenced by things in adjacent regions through interactions that travel at finite speeds. Nothing can instantaneously affect what's happening far away. These 2 principles were so deeply embedded in classical physics that they were rarely even stated. They were just what reality obviously was. Quantum mechanics violates both. We've seen the violation of realism. Quantum systems don't have definite properties before measurement. The act of measurement creates the definite property. This was confirmed by Bell's theorem and its experimental violations. And we've seen the violation of locality. Entangled particles show correlations that cannot be produced by any local mechanism. Together, these 2 violations mean the world is not locally realistic. The Nobel Committee put it exactly this way in 2022 when awarding the prize to Aspect, Clauser, and Zeilinger. The results establish that nature is not locally realistic. The physical world does not consist of locally defined, definite properties. This statement is one of the most radical in the history of science. Confirmed by hundreds of experiments, every conceivable loophole closed. What does the world look like if it isn't locally realistic? The most mathematically straightforward description is the wave function of quantum mechanics. The quantum state of the entire universe is described by one wave function, an impossibly complex mathematical object that contains all possible configurations of all particles, all fields, with specific probability amplitudes for each. The wave function doesn't live in ordinary 3-dimensional space. It lives in an abstract mathematical space whose number of dimensions equals 3 times the number of particles in the universe, a number vastly larger than the number of atoms in the observable universe. This mathematical space is where quantum reality actually lives. The 3-dimensional space we experience with length and width and height is not fundamental. It's an emergent description that becomes relevant for macroscopic objects in classically defined configurations. The underlying reality is a wave function in an abstract space of astronomically many dimensions. The separateness of things in space, the fact that you are here and a galaxy a billion light years away is there, and they have nothing to do with each other, is an emergent, approximate description. It's a very good approximation. It's valid for nearly all practical purposes,
at all scales we ever interact with. But it's not the deepest truth.
David Bohm, working in the 1950s, gave non-locality a striking physical image in his pilot wave interpretation of quantum mechanics. In Bohmian mechanics, particles always have definite positions, but they are guided by a quantum wave that is explicitly non-local. The wave depends on the entire configuration of the universe simultaneously, not on what's nearby, on everything. The influence is instantaneous. The non-locality is explicit. Bohmian mechanics reproduces every experimental prediction of standard quantum mechanics exactly. And there is one more remarkable dimension to quantum non-locality, something that points, perhaps, toward the future of physics. In 2013, Juan Meldacena and Leonard Susskind proposed a radical conjecture. ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, geometric connections between distant points in spacetime. EPR refers to the Einstein-Podolsky-Rosen paper on entanglement. The conjecture is that quantum entanglement between two systems is equivalent to a geometric wormhole connecting them through spacetime. If this is right, and it has support from string theory and the mathematics of the ADS/CFT correspondence, then quantum non-locality is not a strange extra feature grafted onto classical background spacetime. Quantum non-locality is how spacetime is built. Entanglement between quantum systems is what creates the spatial connections between them. Space itself is woven from quantum entanglement. We would not live in a space that has quantum correlations woven into it. We would live in a quantum entanglement structure that at large scales and low energies looks like space. This is speculative. It is theoretical. It may be wrong. But the fact that such an idea is on the table, that quantum non-locality and the geometry of spacetime might be the same thing, is a statement about where physics is right now. At the edge of something. At a moment when the deepest structure of reality might be about to reveal itself. We have 7 laws. 7 laws that are verified beyond doubt. And at the frontier of science, those 7 laws are leading us toward a picture of reality in which space and time themselves are not fundamental, in which quantum connections between systems are what space and time are made of. We are at the beginning of understanding what the universe is. Not the end, the beginning. The universe does not have a fixed nature until something measures it. And the Nobel Committee confirmed in 2022 that this is not a philosophical position. It is a physical fact established by experiment. Local realism is wrong. The universe is quantum. It is non-local. And it is stranger, deeper, and more beautiful than anything that came before. The 5th law is quantum tunneling. The discovery that a particle can arrive on the other side of a barrier it could never classically have enough energy to cross. Not by going around the barrier, not by somehow acquiring extra energy, by tunneling through the barrier itself, passing through solid matter through energy walls, through impenetrable obstacles as if they weren't there. This is not a metaphor. Quantum tunneling is perhaps the most practically consequential quantum effect in the universe. Without it, the sun would not shine. Let me show you the contrast with the classical world first. Imagine rolling a ball toward a hill. If the ball has enough energy, it rolls up and over. If it doesn't, it rolls partway up, stops, and rolls back down. The ball stays on the side it started on. It doesn't matter how long you wait. Without enough energy, the ball never crosses. This is what classical physics says. This is what everyday experience confirms. Quantum mechanics is different. A quantum particle has a wave function. The wave function doesn't stop abruptly at the surface of a barrier.
it penetrates into the barrier. As it enters, it doesn't immediately go to zero, it decays exponentially, getting smaller and smaller as it penetrates deeper. But if the barrier is thin enough, the wave function hasn't decayed to zero by the time it exits the other side, which means there is a non-zero probability of finding the particle on the other side of the barrier. Even if the particle's energy is far less than what's needed to classically overcome the barrier. It doesn't go over, it tunnels through. The probability of tunneling decreases exponentially with the thickness and height of the barrier and with the mass of the particle. Heavier particles tunnel less easily. Thicker and taller barriers suppress tunneling more. But for light electrons at atomic scales, tunneling is routine. It's not a rare curiosity, it's the operating principle of the universe.
The most important place quantum tunneling occurs is in the core of stars.
The sun generates energy through nuclear fusion. Two hydrogen nuclei, two protons fuse together, releasing a burst of energy. This is what powers every star in the sky. The problem is that protons are positively charged, like charges repel. As two protons approach each other, the electromagnetic repulsion grows stronger. To get close enough for the strong nuclear force to fuse them, the protons need to get within about a femtometer of each other. The electromagnetic repulsion at that distance is enormous. It forms the Coulomb barrier. The core of the sun is about 15 million degrees Celsius. At that temperature, protons are moving at roughly 400 kilometers per second. But this is nowhere near fast enough to classically overcome the Coulomb barrier. Classical physics calculates that the protons need to be moving at about 10 times that speed to have any chance. The sun's core is simply not hot enough. If nuclear fusion required classical energy, the sun would not be shining. But the sun does shine, and the reason is quantum tunneling. The protons don't need to classically surmount the Coulomb barrier. They tunnel through it. Their wave functions penetrate the barrier and emerge on the other side, where the strong force takes over and fusion occurs. The probability of any given proton-proton encounter resulting in fusion is staggeringly small. A single proton on average waits about 5 billion years before it successfully tunnels and fuses. 5 billion years per proton. But the sun contains about 10 to the 57th protons, 1 followed by 57 zeros. Even with a fusion probability that low, the total rate of fusion is enormous. Every second, the sun converts about 600 million tons of hydrogen into helium through quantum tunneling. The energy from Einstein's E equals mc squared is what heats the sun and radiates outward as light. Every photon of sunlight that has ever warmed the Earth was created by quantum tunneling.
Every solar day for the past 4.6 billion years has been powered by particles passing through barriers they should never have been able to cross.
Without the wave nature of protons,
without their ability to tunnel through the Coulomb barrier, the sun would be dark. All stars would be dark. There would be no fusion, no stellar nucleosynthesis, no carbon, no oxygen, no iron, no periodic table, no chemistry, no planets, no life. Everything you see, every element in your body, every atom in the universe, heavier than hydrogen, exists because particles tunnel. Tunneling is also the mechanism behind radioactive decay. Alpha particles form inside certain heavy nuclei and would release energy if they could escape, but they're trapped inside the nuclear potential well. Classical physics says they can't escape, but they tunnel out at a rate determined by the geometry of the quantum barrier. This rate gives each radioactive isotope a characteristic half-life. Carbon-14 has a half-life of 5,000
730 years. Uranium-238 has a half-life of 4.5 billion years. The difference is due to the precise geometry of the quantum tunneling barrier in each nucleus. Carbon dating, the method by which we date ancient organic material, by which we know when Egyptian pharaohs lived and when cave paintings were made, works because of quantum tunneling. The scanning tunneling microscope, the first instrument capable of directly imaging individual atoms, uses tunneling as its core operating principle. A sharp metallic tip is brought within a few angstroms of a surface. Electrons in the tip tunnel across the vacuum gap to the surface, producing a measurable current. The current maps out the topography of individual atoms. Every image of an individual atom you have ever seen was produced by this method. The device you're using to listen to or read this script stores data in flash memory. Flash memory works by controlling electrons trapped in isolated quantum structures. Electrons can only enter or exit the storage element by tunneling through an insulating layer. Tunneling keeps the data stable for years. Tunneling is how data is written and erased.
Every time you save a file on a solid-state drive or smartphone, you are controlling quantum tunneling at the level of individual electrons. And there is growing evidence that quantum tunneling plays a role in biology. In enzyme-catalyzed reactions involving the transfer of protons or hydrogen atoms, the observed rates are sometimes too fast to be explained by classical thermal activation alone. Isotope effect measurements, comparing reaction rates with ordinary hydrogen versus heavier isotopes, show signatures consistent with quantum tunneling. Proton tunneling and enzyme active sites may contribute to the extraordinary efficiency of biological catalysis. DNA mutation rates may have a quantum component. Olfaction, the sense of smell, has been proposed to involve quantum tunneling through molecular vibration detection. Life, at its biochemical foundations, may be a quantum phenomenon, optimized by evolution over billions of years to exploit the deepest laws of physics. Particles pass through walls. They power the stars. They create the elements. They store your data. They may run your metabolism. The universe is transparent to things that know how to tunnel. Tonight we explored 7 laws that govern everything that exists. 7 laws that have never once been contradicted by a single experiment in nearly a century of relentless testing. 7 laws that are collectively the most precise and successful physical theory in the history of science. Wave-particle duality. The discovery that everything is both a wave and a particle simultaneously. That light decides what it is based on whether you're watching. That the double-slit experiment, performed now with molecules of over 2,000 atoms, shows interference patterns that can only arise if matter is fundamentally wave-like, and that the presence of which path information instantly destroys that wave behavior. The uncertainty principle. The discovery that nature itself does not simultaneously define both position and momentum. That this incompleteness is not a flaw in our measurements, but a structural feature of quantum reality. That it is the reason atoms are stable, the reason empty space is not empty, the reason absolute zero is not truly still. Quantum superposition. The discovery that quantum systems genuinely exist in all possible states at once until measured. That Bell's theorem and its experimental violations prove that hidden variables cannot explain away this strangeness. That superposition is the foundation of quantum computing, of chemical bonding, of the very stability of matter. Quantum entanglement. The discovery that particles can share a quantum state that transcends space. That measurements on entangled particles are correlated instantaneously across any distance. That the 2022 Nobel Prize in Physics
confirmed at the highest level of scientific recognition that nature is not locally realistic. Quantum tunneling, the discovery that particles pass through barriers they should classically be forever blocked by, that this powers the nuclear fusion in every star in the sky,
that the sun has been shining for 4.6 billion years because protons tunnel through the Coulomb barrier, that tunneling drives radioactive decay, enables scanning tunneling microscopy, and stores the data on your solid-state drive. The observer effect, the discovery that measurement creates rather than reveals physical properties, that the presence of witch path information, not mechanical disturbance but information, destroys quantum interference, that Wheeler's delayed choice experiments show behavior that appears retrocausal within any classical picture, that the measurement problem, why measurements produce definite outcomes, remains after a century unresolved. Quantum non-locality, the discovery that the universe does not consist of locally defined, observer-independent physical properties, that the Nobel Committee confirmed in 2022 that nature is not locally realistic, that the ER equals EPR conjecture suggests quantum entanglement and the geometry of space-time may be the same thing, that space itself may be woven from quantum connections. 7 laws, none of them intuitive, none of them resembling anything in classical mechanics or everyday experience, all of them verified beyond any reasonable scientific doubt by thousands of independent experiments conducted in laboratories around the world. Richard Feynman said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." He wasn't being falsely modest. He meant it. We have the mathematics. The mathematics works. The predictions are correct to 10 decimal places. But the picture, the underlying physical story of what is actually happening, remains after a century of effort, genuinely, profoundly unresolved. Maybe that's okay. Maybe the universe doesn't owe us a story we can visualize. Maybe the mathematics is the reality, and our desire for a narrative is a human need the universe has no obligation to satisfy. Or maybe we're missing something. Maybe there's a deeper layer, a more complete description that will one day make all of this feel as natural and inevitable as Newtonian mechanics feels to us now. This is the dream of many physicists, the quest for a more complete theory. Either way, there is something extraordinary in this situation. Right now, as you lie here, as the room is dark around you, as sleep begins to settle over your thoughts and blur the edges of the day, the atoms in your body, in your skin, and your bones, and your blood, and the neurons of your brain that are slowing now, are not sitting still. They are vibrating with zero-point energy, forbidden from stillness by the uncertainty principle. They are exchanging virtual photons through quantum vacuum fluctuations in the empty space between them. The electrons in their outer shells are in superpositions of energy states constantly resolving and reforming as they interact with thermal radiation. Your body is not a classical object sitting in classical space. Your body is a quantum system so large and so thoroughly decohered that it looks classical. But at the foundation, at the level of the electrons and the protons and the neutrons, it is quantum. It has always been quantum. The universe has never not been quantum. The information in your mind right now, the impressions from this night, the images of double slits
and interference patterns, and quantum tunneling in stellar cores. That information is stored and transmitted through electrochemical processes in neurons that are themselves quantum mechanical systems. Ions tunneling through membrane channels, electrons in molecular bonds, photons absorbed by retinal molecules. The quantum world is not something out there in the distance, in particle accelerators and cryogenic laboratories. The quantum world is here. It is what you are made of. It is what everything is made of. And it defies all explanation. Not in the sense of being supernatural, not in the sense of violating logic, in the sense that every attempt to explain why these laws are the way they are, and not some other way, eventually arrives at a silence. The laws are the laws, because the universe is the universe. We can describe them. We can predict their consequences.
We can harness them in lasers and quantum computers and nuclear power plants and MRI machines. We cannot even now explain why them. Why does observation collapse superpositions? Why can't you know both position and momentum? Why do entangled particles show non-local correlations? Why does the universe have a Planck's constant at all? These are open questions. They have been open for 100 years, and they are magnificent, because they mean the universe is still deeper than we know, still richer, still stranger, that the most successful scientific theory ever created opens onto mysteries that have not yet been resolved and may not be resolved in our lifetimes. Close your eyes. Let the quantum world do what it does in the darkness and the silence, tunneling and interfering and entangling and resolving superpositions, all of it invisible, all of it ceaseless, all of it perfect. The laws are running. They have always been running. 7 laws that defy all explanation, still running, still.
The third law is quantum superposition.
The discovery that quantum systems don't just exist in one state or another, they exist in all possible states simultaneously, a superposition of every possibility until the act of measurement forces them into one specific, definite state. This is the most philosophically disturbing law in physics. It means that reality at the quantum level is undetermined. It is a smear of probabilities. It is a fog of overlapping possibilities. And the fog only condenses into a single, definite fact at the moment something measures it. Let's make this concrete with spin. Quantum particles have a property called spin, an intrinsic quantum property with no classical analog. For electrons, spin has exactly 2 possible values when measured, up or down. Nothing in between. No fractional spin, just up or down. Before you measure what is the spin, classical intuition says it's up or down, you just don't know which. The measurement reveals a pre-existing fact, like finding out which face of a coin landed up. The result is determined before you look. You're just discovering it. Quantum mechanics says, no. Before you measure, the spin is not up or down. It is genuinely, physically, in a superposition of both. There is no hidden fact. There is no underlying reality in which the spin secretly points one way. The particle is in both states simultaneously, with specific probability amplitudes for each. The definite state is not uncovered by measurement. It is created by measurement. This is such a strange claim that it's worth asking how we know it's true. How do we know the spin isn't secretly definite and we just don't know it? This question was taken with extraordinary seriousness. It was the core of a debate lasting from the late 1920s through the 1960s, with Einstein on one side and Bohr on the other.
Einstein argued that quantum mechanics was incomplete. There must be additional hidden variables that, if known, would eliminate the randomness and restore determinism. In 1964, physicist John Stuart Bell found a way to solve this experimentally. He derived mathematical inequalities, Bell's inequalities, that any theory with local hidden variables must satisfy. If particles have definite pre-existing properties, their measurement results must obey Bell's inequalities. Quantum mechanics predicts the inequalities are violated. The experiments were done. First by John Clauser in 1972, then by Alain Aspect in Paris in 1982, with greatly improved controls, then by dozens of subsequent groups with progressively tighter constraints. In 2015, 3 independent groups in Delft, Vienna, and Boulder performed loophole-free Bell tests. Every conceivable escape route was closed. Bell's inequalities are violated every time, without exception. The particles don't have hidden pre-existing spins. Superposition is real. Einstein was wrong. The universe does play dice. The immediate consequence of superposition is that quantum systems aren't just particles or fields or spins. They are probability structures. A superposition of 2 states has measurable consequences that a mere mixture of states doesn't. 2 states that are in superposition can interfere with each other. 2 states that are merely mixed cannot. This distinction is fundamental and experimentally verifiable. Quantum computers are built on this property. A classical bit is either 0 or 1. A quantum bit, qubit, can be in a superposition of 0 and 1 simultaneously. Not 50% chance of one and 50% chance of the other. An actual superposition where the zeroness and oneness coexist and can interfere with each other. 2 qubits in superposition can simultaneously represent all 4 states: 0, 0, 0, 1, 1, 0, and 1, 1. 10 qubits can simultaneously represent 1,024 states. 300 qubits can simultaneously represent more states than there are atoms in the observable universe. Quantum computation exploits this exponential parallelism. Certain problems that would take classical computers longer than the age of the universe to solve can in principle be solved by a sufficiently large quantum computer in hours. Not because quantum computers are just faster classical computers, because they operate on superpositions. They compute all possibilities simultaneously. Superposition isn't only relevant to computation, it's a fundamental feature of chemistry. Chemical bonds form because electrons in atoms can be in superpositions of different energy states. The sigma bonds and pi bonds of organic chemistry, the conjugated systems of aromatic molecules, and the metallic bonding in alloys all arise because electron wave functions can overlap and interfere in specific superposition patterns. The stability of every molecule in your body is a quantum mechanical superposition effect. And then there's photosynthesis. In 2007, Graham Fleming's group at UC Berkeley published a remarkable result in Nature. They were studying the photosynthetic antenna complex of green sulfur bacteria, the molecular structure that captures photons and funnels their energy to the reaction center. What they found was a spectroscopic signature of quantum coherence. The energy absorbed by the antenna complex wasn't hopping randomly from chromophore to chromophore. It was apparently simultaneously exploring multiple pathways in a superposition of different energy transfer routes and finding the most efficient path through quantum interference. The efficiency of photosynthetic energy transfer, over 90% in many organisms, may partly depend on quantum superposition. Life optimized by evolution over billions of years may have learned to exploit quantum mechanics.
And there's Schrödinger's cat. In 1935, Erwin Schrödinger proposed a thought experiment to expose what he saw as an absurdity. A cat in a sealed box. Inside the box is a vial of poison connected to a Geiger counter, connected to a single radioactive atom. If the atom decays, the cat dies. If not, the cat lives. The atom has a 50% probability of decaying in 1 hour. After 1 hour, quantum mechanics says, the atom is in a superposition of decayed and undecayed. The Geiger counter is in a superposition of triggered and untriggered. The mechanism is in a superposition of broken and unbroken.
And the cat is in a superposition of alive and dead, both simultaneously, until the box is opened. Schrödinger intended this as a reductio ad absurdum. He was trying to show how absurd the idea of superposition was. He succeeded in making the absurdity vivid. He did not succeed in escaping it. The mathematical framework of quantum mechanics places no limit on the size of systems that can be in superposition. In 2010, physicists placed a tiny mechanical resonator paddle of aluminum about 15 micrometers long, visible to the naked eye, into a genuine quantum superposition of vibrating and not vibrating simultaneously. It was the largest object ever placed in a confirmed superposition. The team was awarded the Science magazine Breakthrough of the Year. Superposition is real. It operates at every scale. It is the normal state of affairs at the quantum level. Definite singular classical reality is the exception. It is what happens after superposition interacts with an environment and decoheres. It is the settled surface of an ocean of quantum probability underneath.
The sixth law is the observer effect, the discovery that the act of measurement, the act of observation, physically changes the quantum system being observed. Not because measuring disturbs the system in some mechanical way we could in principle reduce to zero, but because prior to observation, the physical properties of quantum systems do not have definite values. They exist as superpositions of possible values, and the act of measurement is what forces one of those possible values into definite existence. We've seen this in every previous chapter. Now, let's look at it directly. Return to the double-slit experiment. When no detector is present to record which slit each electron passes through, the electrons produce an interference pattern. When a detector is present, even one designed to be as minimally invasive as physically possible, the interference pattern disappears. 2 stripes replace the many-striped interference pattern. What the detector does is not mechanical. It doesn't physically push the electrons into different paths. The most carefully engineered detector can be designed to exchange a vanishingly small amount of energy with the passing electron. It can be designed to disturb the electron's trajectory by an unmeasurably small amount. It doesn't matter. If which path information exists anywhere in the universe, if any physical record of which slit the electron used is in principle accessible, the interference is gone. If it isn't accessible, the interference is present. The critical factor is information, not mechanical disturbance. John Wheeler pushed this logic further with his delayed choice experiment. The choice of whether or not to set up which path detection is made after the particle has already passed through the slits. A photon is fired at the double-slit barrier. It passes through.
Then after it's on the other side, after it is classically already committed to a trajectory, the experimenter decides, am I going to ask which slit it went through, or am I going to let it show me the interference pattern? If the experimenter sets up which path detection after the fact, the photon behaves as a particle, as if it had always traveled through one slit. If the experimenter sets up interference measurement after the fact, the photon shows interference as if it had always traveled through both slits. The decision made after the photon has passed the slits seems to determine what the photon did at the slits. Wheeler's delayed choice experiment was performed in 1984. In 2007, with greater precision. In 2015, with single photons in a comprehensive delayed choice quantum erasure configuration. The results always confirm Wheeler's prediction. The photon's behavior is determined by what the experimenter chooses to measure, even if that choice comes after the photon has already passed the measurement apparatus. This does not mean the future causes the past in a causally paradoxical sense. Quantum mechanics is internally consistent. No actual paradoxes arise. No information travels backward in time. But the picture it gives of physical reality is deeply strange. There is no story of what the photon did between leaving the source and being detected. The photon does not have a definite history until the history is fixed by a measurement. The measurement creates the history. John von Neumann, in his rigorous 1932 mathematical formulation of quantum mechanics, analyzed where in the measurement process the quantum superposition collapses. He considered every component of a measuring apparatus and showed that each one is itself a quantum system. The quantum superposition isn't eliminated at the detector. It propagates through the detector into its output, through the amplifier, through every stage of the measurement chain. The chain of superposition extends outward indefinitely through every physical system it touches. Von Neumann concluded that within the strict mathematical framework of quantum mechanics, the superposition is only interrupted at one point, the observer's conscious experience.
This was not von Neumann casually speculating. It was a rigorous mathematical conclusion. He was saying, if quantum mechanics applies to everything physical, then consciousness must play a special role because it's the only thing in the formalism that isn't subject to quantum superposition. Most physicists today don't accept this conclusion. The development of decoherence theory provides a way to understand the emergence of classical behavior without invoking consciousness. As soon as a quantum system interacts with its environment, air molecules, photons, electric and magnetic fields, its superposition becomes entangled with so many degrees of freedom so rapidly that it becomes effectively impossible to observe the interference effects. The superposition spreads out into the environment and the system looks classical. But decoherence explains why quantum systems look classical. It does not explain why quantum systems produce definite outcomes. When the cat decoheres, it becomes entangled with the environment in a superposition that looks classical. But mathematically, the superposition is still there, spread across the quantum state of the entire environment. The question of why any given measurement produces a definite result, not just why it looks definite, is called the measurement problem, and it remains unresolved. After nearly a century of quantum mechanics, nobody has given a fully satisfying answer. In recent years, experiments have directly probed the quantum to classical transition. In 2021, groups at Caltech and MIT simultaneously demonstrated quantum entanglement between a microscopic mechanical oscillator and a photon. The mechanical oscillator, a tiny vibrating drum made of a few trillion atoms, was entangled with a single photon. Measuring the photon instantly collapsed the mechanical oscillator into a definite state. An object with trillions of atoms placed in a quantum entangled state with a single photon. The quantum to classical boundary is being pushed. The measurement problem is being tested directly. Theoretically, some physicists believe quantum gravity will resolve the measurement problem.
Roger Penrose has proposed that the superposition of two distinct mass configurations is inherently unstable because it would require space-time itself to be in a superposition, and that quantum gravitational processes cause collapse at a specific scale. This is called objective collapse. Experiments are being designed to test it. The measurement problem remains open.
The relationship between consciousness and physics remains mysterious. All of this vast, unfinished landscape was opened up by the simple experimental fact that an electron builds an interference pattern when you don't watch, and two stripes when you do. The observer and the observed are not separate. The question and the answer are not independent. The universe and the mind that studies it are in some deep sense still being worked out in conversation. The universe responds to questions. It gives answers. And those answers are not found. They are created. Somewhere in the gap between those two statements lies one of the deepest unsolved problems in the philosophy of physics. The observer effect is not mysticism. It is physics. Unsettling, unresolved, deeply mysterious physics. But physics.